Hi, I'm Sengstacken, a machine learning specialist, solutions architect at AWS. Today we're going to cover how to build trustworthy machine learning applications by detecting and monitoring bias in machine learning models. We're also going to cover explainability in these machine learning models. So to get started, let's first discuss the agenda for today. We're going to be deep diving into machine learning bias and explainability. I'm first going to provide a background on bias in machine learning. Where can it come from, and where in the machine learning workflow should you expect to monitor for bias? If we want to understand the why and the how bias is occurring in a machine learning problem, we also need to understand explainability. And I'm going to provide an overview of machine learning explainability. Once we understand the background on bias and explainability in machine learning models, we're going to take a look at a new feature called Amazon SageMaker Clarify for monitoring machine learning bias and providing out-of-the-box explainability. I'll show you how to use Amazon SageMaker Clarify in a quick demo. And then lastly, we're going to recap everything that we've learned today. We'll provide some additional information on how you can get started monitoring your machine learning workflows for bias and explainability. Let's get started. Okay, so to start, let's talk about understanding the background in bias. What is bias in machine learning, and where could it come from? Bias in machine learning is a result or prediction that is systemically predisposed or partial due to faulty assumptions. And in many cases, bias in machine learning can cause an algorithm to miss the relevant relationships between features and targets. In machine learning terminology, this could be referred to as underfitting. Machine learning models, especially those that make predictions that serve end customers, are at risk of being biased and producing harmful or incorrect outcomes if the proper precautions are not taken. This makes monitoring and detecting bias across the machine learning lifecycle a critical step in your machine learning workflow. And bias can show up in any stage of the machine learning workflow. For example, in data collection, in data labeling, training data preparation, in a trained model, and then even when we deploy that model to production. And bias is not a new term or concept when it comes to machine learning or mathematical modeling. Right? For example, bias has been studied for many years in the design of experiments and in psychology. Additionally, just as machine learning workflow is not static and complete once we deploy a model, neither is your work in monitoring and analyzing your machine learning application for bias. This is a continuous process. So let's look at some of the ways that bias may be present in a model. So before we train a machine learning model, the initial data that we're going to use for the model might contain imbalances, such as not having enough examples of members of a certain class, which can then cause the model to become biased against that class. And research has shown that machine learning models have the ability to amplify bias. We're going to refer to this as pre-training data bias. Another example is when your model might develop bias behavior during the training process. As an example, let's consider a machine learning model that's used for bank loan approval. We're going to come back to this example multiple times today. The model might use bank location, the location of a single bank branch, as a positive indicator to approve a loan as opposed to the actual financial data if one particular bank approves more loans than others. And in this case, the model has become biased towards the applicants that apply at that location and against the applicants that do not. This is regardless of their financial standing. Let's refer to this as post-training bias. And then finally, bias may develop over time as the real world begins to deviate from the data that was used to train your deployed model. Let's continue this example of a bank loan approval. And if the model has been trained on an outdated set of historical mortgage rates, it might start to become biased against home loan applicants as the mortgage rates and fiscal landscape have changed over time. We're going to refer to this as deployed model bias. Okay, so we've defined pre-training data bias, post-training data bias, and deployed model bias. Let's take a closer look at the pre-training data bias. Said differently, This is the data that we're going to train our model on.
In the simple example of a bank loan approval model, imagine that one of the features or inputs to the model is the applicant's age. We might transform this input variable from a continuous variable into a categorical variable via binning. This means we're now dealing with categories of ages. Examples 30 to 40-year-olds, 50 to 60-year-olds. And if we take a look at the bins of these ages, we want to inspect the overall number of examples in the training data set. So let's take a look at the 30 to 40-year-olds versus the 80 to 90-year-olds. And again, these are age bins. So for the 30 to 40-year-olds, we have many more examples in the training data set as compared to the 80 to 90-year-old class. And you can inspect the balance of these classes by using this simple bar chart. The class imbalance might contribute to the machine learning model from loan approval to become biased against an underrepresented class. You might also look at the class distribution as a function of predictive class. So for each of these bins, how many were approved or denied for their loan? And if we take a look at the classes as a function of the predictive class, using the same age bin examples of 30 to 40-year-olds and 80 to 90-year-olds. Now if we look at which loans were approved and which ones were denied, and if we normalize these data sets, we can see for the 30 to 40-year-old class, we have a roughly even distribution of examples in our training data set where the loans were both approved and denied. But for the 80 to 90-year-old class, we see many more examples on where the loans were approved, but many fewer examples where the loans were denied. And again, we want to check the balance of these data sets as we're using them for a machine learning model. How many examples in total in the training data set were approved versus denied? Understanding this distribution also of the predictive class informs us which loss or metric we should use for optimizing and scoring the various machine learning models. So again, this is pre-training data bias, but recall that bias can also show up during the training portion and prediction portion of machine learning lifecycle. We'll show you how to monitor that a bit later. So how do we understand why bias is occurring in our machine learning model? Well, to understand why, we need to take a look at explainability of machine learning models.
So why is a machine learning model making a prediction? This is referred to as explainability. And one of the common criticisms of machine learning models is that they're black boxes, in the sense that they make good, valid predictions, but understanding why they made predictions, what was the logic behind that prediction, you can't understand. And this statement might be true in some cases where data science teams might not know how to extract insights from their models, might not know how to assess explainability of their machine learning models. Today, we're going to show you how to understand the why behind a machine learning model prediction. When you train a machine learning model, you might ask, after you train this model, what features had the biggest impact on the predictions? What features are the most important? Additionally, for a single prediction, you might ask, why did the machine learning model make that prediction? There's a number of different approaches that you can use for explainability and feature importance. But in the end, this is a critical step of understanding interpretability and explainability for a machine learning model. Explainability is useful for more than just bias assessment as well. And let me explain this. Many regulators might need to understand why a machine learning model made a prediction. Was that prediction free from bias, both in the training and in the inference or the prediction? You might also need to provide internal stakeholders. Maybe this is a customer service rep or a loan officer or even an end customer an explanation on why did the machine learning model make a prediction. To use the example of a loan officer, you might need help to explain why to the customer the loan was approved or denied. What factors caused the machine learning model to make that prediction? And then finally, the data science team itself can improve models and get a deeper understanding on whether a model is making the right inference or prediction for the right reason. Perhaps irrelevant data points are being used, and that's altering the model behavior. Like, for example, inspecting the feature importance of a trained model can also improve the understanding of this model for the data science team. Many times you might identify data leakage or outliers when you review the feature importance. You're going to see features that you didn't expect to be as important as they are. This can give the data science team a greater understanding of what's happening within the machine learning model. So let's dive deeper on what it means to assess a machine learning model for explainability.
So why is the machine learning model making a prediction? Well, to understand the why, let's first ask ourselves, what features are driving the prediction? What features are most important to the model? This type of question is known as feature importance. There are many ways to calculate feature importance on a machine learning model, but two approaches that I like to use are either global SHAP values and permutation importance. And to look at feature importance, we're going to list all of the input variables that we use in our machine learning model. So in our bank loan example, we'll use location, we use the applicant's age, use income, and credit history. And as we look at the global SHAP values for these different variables, we can plot these SHAP values using a simple bar chart. So in this hypothetical example, you can see that credit history was the most important variable, the most important feature based off on our training data set if we take a look at global SHAP values. Income was a close second, age was third, and location had very little importance to the overall machine learning model. All right, so this is again globally. What about an individual prediction? How can we explain why the model made a prediction for a specific set of inputs? There are various visualization strategies for interpreting individual predictions. For an individual prediction, I like to use a waterfall plot. So to make a waterfall plot, we will start again by listing the features. So we'll have income, credit, age, and location. Now, a waterfall plot starts at the expected value, also known sometimes as the baseline of the machine learning model. So here we'll assume in this hypothetical example that the baseline or the expected value of the model is 0.5. And we look at the individual contributions of each input variable. So location had a negative contribution of 0.05. Next, we come up to age. Age also, in this hypothetical example, had a negative contribution of 0.15. As we come to credit for this example, right, the single individual that applied for a loan, credit in this example had a positive contribution. And this was plus 0.3. And income even had a larger positive contribution of plus 0.35. So we can look at the additive effects of each input variable to get the overall prediction. So in this example, it was 0.95. And we can look at the individual effect of each input variable about why the machine learning model made the prediction, right? This loan was approved because the income and the credit variables for this example gave positive direction. Right, this gives data science teams also insight to how much each feature is contributing to the model prediction. Okay, so we've discussed the background in bias and explainability. So what are the challenges with bias and explainability in machine learning workloads today? Why isn't this commonplace? Well, the first of all is complexity. Right? This can be a multi-step process where you're evaluating bias at the data preparation stage, at the model training stage, and then even once the model is deployed. And you're looking at explainability on the trained model. Could rely on custom code, custom libraries. There are many libraries available, but could be a manual process.
So to address these issues of complexity, custom code, and manual processes, today I'd like to introduce Amazon SageMaker Clarify. Amazon SageMaker Clarify is a new feature that helps customers understand and quantify the bias in their data sets and trained model. Clarify also provides explainability for machine learning models. SageMaker Clarify is integrated with SageMaker Data Wrangler, so it makes it easy to identify bias during your data preparation. You simply select the attributes of interest, and SageMaker Clarify runs a set of algorithms to detect the presence of bias in those attributes. After the algorithm runs, SageMaker Clarify provides a visual report with a description of the sources and severity of possible biases, so you can take steps to mitigate it. And as you train your model, it's important to check for biases to ensure that predictions are fair, such as ensuring that one protected class is not denied services more frequently than another. Amazon SageMaker Clarify is integrated with SageMaker Experiments. So after your model has been trained, you can identify attributes that you'd like to check for bias. And SageMaker runs a set of algorithms to check the trained model and provide you with a visual report on the different types of biases for each attribute. And finally, once you deploy a model, changes in the world may develop bias over time. SageMaker Clarify is integrated with SageMaker Model Monitor, enabling you to configure alerting systems like Amazon CloudWatch to notify you and your engineering team if your model begins to develop bias. So that's on the bias side. For explainability, Amazon SageMaker Clarify will provide a graph detailing the importance of each input for the model's overall decision-making process. These details can help you meet compliance requirements and determine if a particular model input has more influence than it should on the overall model behavior. Lastly, Clarify can be integrated with Amazon SageMaker pipelines for reproducible bias and explainability jobs, and there's no additional cost for using Amazon SageMaker Clarify. It's available today. So let's take a quick look at a demo on how to use Amazon SageMaker Clarify. So in this demo, we're going to use an example from the AWS GitHub repo for how to use Amazon SageMaker Clarify. So I have the Jupyter Notebook pulled up in Amazon SageMaker Studio. This is one way you could interact with Amazon SageMaker Clarify. So let's step through this. So the overview of this problem in the Jupyter Notebook is that we're going to use census data to predict with a binary classifier whether or not an individual makes more than $50,000 a year. So true or false, does the individual make more than $50,000 a year? And we're going to use census data. This data set comes from the UCI repository, a popular location for a lot of data science public data sets. And as an input to this model, we'll use attributes such as age and work class and education and marital status and ethnic group and relationship and country. These are all the attributes that were collected as part of the census data. So the first thing that we're going to do is we'll read in this data set. We'll read it in to SageMaker, and we'll also set up Amazon SageMaker. We're going to read in the data set using a popular library called pandas, where we'll read in both the data set and a training data set and a testing data set. And here's an example of what this data set looks like, where we have age and work class and education, marital status, occupation, just to name a few. Our target category that we're predicting is the last column here, the target class, whether or not an individual makes more than $50,000 a year. And this example is really not about training the model. That's not the goal of this example. The goal is, how do we assess the model, the data, and the deployed model for bias, and how do we also provide explainability? So one of the first things we might do as a data science practitioner is inspect the data that we're going to use to build the model. So here's an example of the distribution of the number of counts. This is a simple bar chart between male and female examples in the data set. And you can see already that there's a 2-to-1 ratio between male examples and female examples in this data set. Not highly imbalanced, but it is imbalanced of a data set. And if we take a look as a function of the predictive variable, again, our predictive variable here that we're going to be predicting as part of our binary classification problem is whether or not an individual makes more than $50,000 per year. If we take a look at the difference between male and female examples for positive examples of the target, examples where that individual made more than $50,000 a year, we can see that the data set becomes even more imbalanced with a 6-to-1 ratio between males and females. Okay, so we haven't used SageMaker yet. We haven't used SageMaker Clarify to assess this model, but we're being good data scientists and taking a look at the data distribution prior to modeling. So the next step that we do is we encode our data, right? Our machine learning models use numerical data versus strings or categorical data. So we're going to encode our data with integers that will represent the input data, the training data. One of the things that we have to do if we want to train a model with Amazon SageMaker is we want to upload that data to S3. So we upload the data to S3, and we configure our estimator. Our estimator for this example is going to be a gradient boosted trees example. We'll use the XGBoost algorithm that's built in to SageMaker. And again, we're going to train this model using a binary classification screen. True or false, did the individual make more than $50,000 a year? We'll train this model using a training job with Amazon SageMaker, and we'll register the model, but we don't have to deploy it to use Amazon SageMaker Clarify. We could deploy it, but we don't have to. And in this case, we aren't going to deploy it fully yet. So the real heart of this example is, how do we use Amazon SageMaker Clarify? And at the heart of Amazon SageMaker Clarify is really a processing job. Processing job that's going to run a number of algorithms both on our pre-training and our post-training to look for bias. And we can specify which bias analysis we're interested in. So first, we'll instantiate the Clarify processor. And just like with the training job in SageMaker, we'll have to specify an instance type and a SageMaker session and an instance count. Once we have the Clarify processor instantiated, we want to configure Clarify to measure and inspect for pre-training data bias with our data config, and also post-training data bias with our model config. We're going to be focused here on the gender of these examples, males versus females. Is there bias in that data set, especially as it relates to the target variable? We're going to configure our bias metrics, and in Clarify parlance, this is referred to as the facet. So here we'll configure the bias metrics with a facet of sex for male versus female. And then finally, we'll run our bias training job. We're going to be looking at all of the methods, all of the algorithms for pre-training bias, and all of the methods for post-training data bias. You have the option to specify which algorithms you're interested in, which metrics you're interested to measure bias. Here the clarify processing job completes, and as it runs, you'll get standard out printed to the screen with the different bias measurements. This is in JSON format, and we don't want to look at JSON format. So what we can do is we can use SageMaker Studio. Because SageMaker Clarify is integrated with experiments, we can look at the explainability using a nice report. Again, this is under the SageMaker Experiments portion of SageMaker Studio. And here we see the output of our bias analysis for pre-training data, right? Where the class imbalance was detected. We already knew this because we took a look at the data ahead of time, but if you didn't, you could automatically detect class imbalance. We see that there's a difference in positive proportions of the labels, yet again, another metric that we might be interested in. And as we look at these statistical measures, we can also use a drop-down to get a greater understanding of what do these measurements mean. These can be new to some data science teams. This is not the only way to view this report. Like I mentioned at the beginning, SageMaker Studio is one option that we have for running Clarify jobs. As part of the Clarify job, we specify an output path. And SageMaker Clarify will put the bias report into S3, and we can see the report here. We have an HTML version, a PDF version, and a Jupyter Notebook version. So multiple different formats to support our analysis because we don't want to look at the JSON output and standard out. So here's an example of what this analysis report, if we take a look at the PDF file that was uploaded to S3. So again, multiple ways to measure bias using Clarify processing jobs. And again, these can be integrated with SageMaker pipelines. So this can be an automated process from data transformation, model preparation, model training, pre and post-training bias detection, and then finally model deployment. Okay, so that's on the bias side of Amazon SageMaker Clarify. How about explainability? So we can use Clarify for explainability just as we used it for bias detection. And just to recap, remember that explainability is the why a machine learning model is making a prediction. What features are most important? And for this example with Amazon SageMaker Clarify, we're going to be using the statistical concept of SHAP values. SHAP values are a common way to measure explainability and how your model predictions would deviate from the baseline or the expected value of that model. So the first thing that we want to do is we want to configure Clarify with our SHAP configuration. We want to provide an output path and then also a data configuration about where our training data lives. And then we'll run the explainability job. Just as we ran the bias detection job, the explainability job will output metrics to the standard out. Again, this is JSON format. And again, this is not what we want to read. This is, while it is human readable, it's not nicely formatted. So again, we can use SageMaker Studio. Because Clarify is integrated with experiments, we can take a look at this report, model explainability report. And this is captured as part of the model. We can always go back to this experiment and look at the model explainability as part of the experiment tracking. And here we can see, using SHAP values, which features were most important to our binary classification model for predicting whether or not an individual made more than $50,000 a year. Here you can see that capital gains as an input value was the #1 feature for importance. And then age, relationship, marital status decreased as you go down. But you can see from this which features are most important to that machine learning model and why is a machine learning model making a prediction. And just as we showed earlier with the bias detection, S3 also is capturing the output location of Clarify explainability jobs. And we can see PDF files, HTML files, and a Jupyter Notebook that captures the report. Here's the example, that same example that we looked at SageMaker Studio, but now we're capturing global SHAP values in a PDF report. All right, so this is a powerful example of how to use Amazon SageMaker Clarify, and it gives you a good basis for understanding how to integrate bias detection and explainability in your machine learning workflows. So to recap, we've discussed how monitoring for bias is a critical task within the machine learning workflow. From data preparation to model deployment and monitoring, recall that machine learning training has the opportunity to amplify bias. And it's important as a machine learning practitioner to understand the bias in our data that we're using to train the model and also in the trained model themselves. We showed you how to use Amazon SageMaker Clarify to analyze a data set, a trained model, and a deployed model for bias detection. And we discussed how to gain insights and understanding from your machine learning model using model explainability. We also showed how to use Amazon SageMaker Clarify to measure explainability on your trained and deployed model. If you're interested in reading more about Amazon SageMaker Clarify, check out the documentation online and the links above. We've also published a detailed white paper that covers the bias and explainability metrics that are calculated, including the formulas that are used. And lastly, there's a great blog post by Julian Simon and a video by Julian Simon on how to use Amazon SageMaker Clarify to increase the transparency of your machine learning models. And in addition to these great resources, also check out the AWS GitHub. That repo has many hands-on examples on how to use Amazon SageMaker Clarify. These examples in the GitHub repo are usually my go-to resource for learning a new feature or function that gets introduced to the machine learning stack at AWS. So you joined the AWS Summit today to learn, and you can keep learning after the summit is over with resources from the AWS training and certification team. We offer over 65 different courses. Many of them are free and available on demand, as well as virtual and instructor-led training. AWS experts will help you and your team apply machine learning to your business applications. When you're ready, you can also pursue the AWS certification in machine learning. This validates your skills and provides an industry-recognized credential on machine learning. For more information, check out the URL above, but also check out the AWS Ramp-Up Guide to learn more. I want to thank you for your time today, and thanks for joining the Public Sector Summit.